let's compute the MLE, the maximum likelihood estimate, for linear regression. So for a maximum likelihood estimate, we need to have some data. So let's set things up for computing an MLE. So we've got some data, and since linear regression is a supervised problem, it's x1s and so it's x's and y's. We got x1, y1 up through xn, yn, and each of these xi's is a point in, say, d-dimensional real space, and each of the y's is just a real number. So we are given some data, and we need to assume some probabilistic model. And under linear regression, the model that we assume is that we assume that we have some random y's. So remember, for linear regression, the setup was that we had y, a generic y, distributed as a normal random variable with mean w transpose x, where x was the corresponding point for that y, and mean sigma squared. So here, let's see. So let's assume. So this is, to be precise, this is for Gaussian linear regression, and let's assume that this variance is known, this sigma squared. So we're going to assume. So assume sigma squared is known, and then we're just going to find the MLE for w. So normally, remember, in linear regression, our parameters, theta, would be the pair w and sigma squared, but it'll just be w in this case since we're assuming this is known. Okay, so that's the generic thing, and now to model our data, we're going to assume these random variables y1 through yn, and we assume they're independent. And yi is just like this, normal with mean w transpose xi and variance sigma squared. Okay, so yeah, so independence is part of our assumption. And for the MLE, so to compute the MLE, what's the MLE? Well, an MLE, a maximum likelihood estimate, is a maximizer. It's an argmax over thetas, over all the possible thetas. So let's see, capital theta, in this case, since theta is just w, that's all the possible w's, and that's just our d in this case, since w lives in the same space as these xi's. So it's a value, the MLE is a value which maximizes the likelihood, the probability of the data given theta. And so to be a little more precise here, maybe I should write, because it's not necessarily unique, so usually people think of this as a set rather than just a value, since it's not necessarily unique, if it's not necessarily unique. So to be more precise, we want to find a value in the set of maximizers. Okay, so now we need to write this likelihood function in terms of our model. So how are we going to do that? Let's see. So this is our setup here. So let's see if we can write this likelihood. So this is the probability of all these points. And now under this model, the x's are not random. The only thing that's random is the y's. So this is equivalent. So sometimes people condition on x here, on the x's, to define the likelihood function. But to try to be consistent with our previous notation, you could think about, like each of you could have some random variables xi, that's where xi equals our observed values with probability 1, for example. That's the same thing. It's basically it's the same thing basically as conditioning. So it's the probability of the y's given the x's and theta. And since these are independent, it's the product of the probabilities as I goes from 1 to n of probability that yi equals little yi. And since yi depends only on xi, both in it, well, if xi is not random, then not dependent in a statistical or probabilistic sense, but just functionally dependent, right? Because writing it this way, since technically speaking, we don't have a distribution on theta and all. This is just, remember, this is a notational device to say that these distributions are parameterized by theta. So functionally, yi only depends on xi, and we can drop the dependence on the other x's. Okay, so now what is this? What is this? What are these factors here? Well, that's what our model tells us. So our model tells us that yi is normal, and we can write these so that each of these, so this is a product of these normal densities. And let's go ahead and maybe we'll just go ahead and write out what they are. So it's a normal, so it's 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared. The mean is, it's the value is yi, so it's yi minus the mean, which is w transpose xi. That difference squared. All right. Okay, so that's looking good. We got a good expression for our likelihood function. And now we'll do the usual trick of taking the logs. It looks like it's going to be very useful here. Should we do that first, or should we? Actually, let's write one more line here. Let's pull together some things first. So all these factors are the same over the n product, so this is just that thing to the nth power. And the product of the exponentials, we can pull together all the exponents, and so that becomes the sum of all these exponents. And we can pull out this 1 over 2 sigma squared minus 1 over 2 sigma squared. We get the sum as I goes from 1 to n yi minus w transpose xi squared. Okay. So now so we're probably going to take logs in a minute, but first, before we jump to that, let's think about what this expression is. This is where y enters where w enters into things, and that's what we're interested in maximizing. So let's see if we can rewrite this sum in a different way, in a nicer way maybe. So this is So this is a sum of squares. So if we have some numbers, say ai, and we take the sum of their squares, that's equal to, if we made a vector out of these, that would be the dot product of a with itself. If a was the vector of the ai's, the column vector. So this is a sum of squares, right? Each of these yi's is just a real number. It's the value, and the w and xi, the dot product of those, is just a number. So this is just a sum of squares. So let's see if we can. So let's think about this. So the vector here, right? This vector a in this case is going to be y. We can line up all these quantities into a vector. So it's y1 minus w transpose x1 to yn minus w transpose xn. We just put these into a column vector. And this equals, we can break off the y part and the other part here, the W transpose X part. Oh, that's a 1. W transpose XN. And this, let's give this a name. This is just the vector of y's. So let's call that, well, I'd like to call it y, but I think we already used y for, well, we tend to use little y for just the value. I guess we haven't used it here, so let's just call that y. So this is just y. This is the vector of y, of the y's. And sometimes I use little y for a single value, but here, remember, it's a vector, column vector. And this part here, actually, right, we can always, W transpose xi equals xi transpose w, because this is a scalar quantity, and the transpose of a scalar is itself. This is the transpose. So let's switch these. Let's make it, I think that's going to be a little bit, make our life a little easier. So these are now xi transpose w. And we can pull out the w here. So this we can write as x1, the vector of x1 transpose down to xn transpose times w. I think that's right, because, right, so this is a matrix. Each of these is a row in the matrix. And this is just the definition of multiplying a matrix times a column vector, right? You take the first row, you take the dot product, and that gives you the first entry, and so on. So let's give this matrix. This is a matrix. Let's give it a name. That's something that we'd like to work with. So let's call it A. So A is, let me write what A is. A is this matrix x1 transpose down to xn transpose. And this is sometimes called the design matrix. That's what this A is. Okay, so now we've got our nice expression. So we've simplified this thing. Well, we've simplified, right? So okay, we've written this to this sum here. The sum of the squares is the, remember, right? That was by our observation here. That was just the dot product of this vector with itself. So that means, back up to here, that sum, I'll just write it here for our. So the sum of yi minus w transpose xi squared equals the dot product of this vector, y minus aw, with itself. So that's, we can also write as, well, I'll write it two ways. It's y minus aw transpose times y minus aw. And that's also equal to the Euclidean norm of y minus aw squared. Okay, so now, so let's, all right, we're running out of time in this video, but we're going to, so let's stop there and we'll pick it up in the next video. All right, see you soon.